So next up we have Ryan Williams, who's going to tell us about the complexity of solving systems of polynomial equations.
Thanks for the introduction. Thanks for coming. So by invoking this fine-grained adjective, I'm going to allow for algorithms which slightly beat exhaustive search for solving systems. And I'm going to talk about conjectures and hardness results for slightly beating exhaustive search. So the reason I wanted to speak about this is it has some proofs and ideas which I think would be of interest to this audience. So let's start with the problem. So in this talk we'll be looking at mainly prime fields, so fp where p is prime and k be some positive integer. We'll look at degree k fp system solvability, where you're given a set of m polynomials and n variables whose degrees are at most k, and we want to know if there's a solution to them. So if there is some assignment to the variables which, say, makes all the polynomials vanish. Is the zero set empty or not? Okay. So in this talk we'll think of p and k as small, like constants, and n as quite large, and p is, say, smaller than k. Okay. So or say much smaller than like exponential in k. So this particular setting of parameters is of interest for various crypto systems, like, for example, like quadratic systems of equations, where like a crypto system is based on the hardness of solving a quadratic system. So just to get used to this notation, so if I have degree 1, it's linear equations, and then I can solve this problem in P by Gaussian elimination. If I only have one equation, then I'm just trying to find a root of 1 degree k polynomial, which would say, and I'm giving you the list of coefficients, the monomials explicitly, and this is finding a root, so this you can solve in polynomial time. But if I allow you arbitrarily many equations and I look at f2, degree 2, it's already NP hard. So the easiest way to see this is a reduction from a not equals 3 set. So I do want to say that there are quite a few algorithms known when n is small. So for example, Niraj gave a talk at Simon's several years ago, an algorithm which runs in time which is polynomial for a fixed n. But it's degree to the some exponential in term time. Right? But for our case, where we're looking at just some finite field like fp, we have n variables. We want to know if we can beat p to the n. Just the brute force algorithm of trying all the possible assignments. And so something that was started in the fine-grained semester at Simon's in 2015 and eventually worked out with Lokshanov, Paturi, Tamaki, Huacheng Yu, and myself, is that yes, you can beat exhaustive search. This particular running time, so it's p to the n divided by p to the n divided by order k, some factor in terms of k. It gets worse as k grows, the improvement of exhaustive search. And if this is true for like p, which is not too large as a function of k, whenever p is greater, you still get some improvement over exhaustive search, though it's slightly worse. Okay. So the first thing I want to do is tell you about this algorithm. Okay. So there's the problem again and the statement. So I was trying to think of how to explain this algorithm in some clear and succinct way, and eventually I just decided I would constrain myself to one slide. So, but I mean, I guess the slide. Yeah. Well, there's a very interesting use of white space, I guess you could say. We'll see. Literally, okay, white space. Yeah, fine grain exposition. Right. Well, this is actually going to be coarse grain. That was actually my point, was that it was getting too technical, so I wanted to be coarse grain. Okay, yeah. So the general idea behind this algorithm, what makes it different, I think, from lots of other types of algorithms for this problem, is to approach this in a circuit complexity way. Okay, so try to define a kind of circuit. This is some hybrid between a Boolean circuit and a circuit that takes values from fp as input. and then try to massage the circuit and do some interesting evaluation on the circuit. So that's the general idea. Okay, so we're given a set of polynomials. So these are, again, degree k polynomials. And I partition mentally the set of variables into, say, delta n variables and n minus delta n variables for some parameter delta. Okay. And so I'm going to define a n minus delta n input circuit. So that's going to be on the x variables. Okay. And the idea, so this circuit is doing what? It's taking an OR over all possible assignments to the y variables. Okay. So all possible delta n vectors. It's sticking that assignment in for the y variables. It's checking whether for all equations that equation is 0. So this bracket is just the indicator which outputs 1 or 0 depending on whether the predicate inside is true. Okay. So it's just brute forcing, but over p to the delta n partial assignments. Okay. All right, so this is a circuit that takes in fp values but outputs a true-false value. Okay? But we can think of that as a 0-1 value. So, all right. And so the observation is, well, satisfiability for this circuit, what does that correspond to? So it corresponds to finding a setting to the rest of the variables, so some b vector on n minus delta n variables that makes this thing parent 1. And that's going to exist if and only if there is a solution to the whole system. This is just sort of obvious. I mean, it's brute forcing over delta n the variable. So if I manage to find something which makes these things true on the rest of the variables, then there is a solution to the whole set. Okay. All right. All right. So now I want to sort of solve the SAT problem for this kind of circuit. That's the idea. Okay. Where it takes in values from fp and outputs a true-false value. I want to solve the satisfiability problem. So adapting this sort of well-known circuit complexity work of Rozborov and Smolensky, there is a way to randomly reduce such a circuit, so even this sort of hybrid Boolean and FP circuit, to a polynomial of degree which is not too large. So here it's p times delta times n times k, but it's a single polynomial. Okay? So that for any particular input I might give to this circuit, this polynomial will output the correct value in some sense with high probability. So what do I mean by that? I mean that whenever I stick in a b, so this is a worst case type thing. So for all b, when I stick in a b, it's going to be 1. So if it's 1, then the choice over the randomness of this q sub s b will be non-zero with probability greater than 2/3. Okay, so this thing will be non-zero with probability greater than 2/3. And this randomness, again, is over the choice of the q sub s, not over the particular assignment. And when it's 0, the probability, this is 0, this should be greater than 2/3 as well. Okay. So the point is that like the non-zeroness is telling us whether it's true or false with some decent probability. Okay. And at a high level, the way this kind of thing works is it's just anybody who's familiar with the Rozborov-Smolensky construction could work this out very easily as an exercise. The idea is what they show is for an OR and for an AND, you can represent them with probabilistic polynomials of low degree. Okay, and there's some trade-off between the degree that you'd like to have and the error of the polynomial, sort of like the probability of error. And so the idea is you just form appropriate probabilistic polynomials for the and for the or. Here you only really need constant degree to achieve this kind of error. Here you would want a larger degree. So degree so you can union bound over all of these things. So like delta n k roughly degree. And so just replacing these two things with probabilistic polynomials, you can get this result. It's
So are you doing a union bound over all the b's or?
No. Over all the different terms in here. So like you want to say I have a probabilistic polynomial which has this property. Right.
The statement be for all b, I can randomly reduce.
It's a worst case randomized algorithm. So it's like in the worst case, no matter what input I've got, the probability gives me the right answer over the choice of internal randomness. The probabilistic polynomial is high.
But,
Yeah.
but the quantifiers are B comes first and the random choice of Q sub S is
Yes.
next. Okay.
Yes, yes, yes. So yeah, all I was saying is you would want the degree of your probabilistic polynomial to be, say, constant for the OR and something like delta n for this one, so you can account for all the different possible errors you might get, because there's like p to the delta n different things you have to account for there. That's all.
All right.
Yes?
Just as a historical comment, maybe two. First of all, this part is this reduction from the Boolean case to the arithmetic case is the part in Razlov's paper that Smolensky.
For mod 2, yes.
Yeah.
For mod 2.
No, the other part in Smolensky's paper is doing the low bound.
For mod 2, yes.
Yeah, it doesn't matter what fit it was. Yeah, but the
Yeah,
other,
it does matter here. So
no,
p
no,
is
no. Yeah,
arbitrary.
I'm
So
saying the reduction is the same for every field.
no, it's not. That's why there's a p there.
Yeah, no. The reduction to a probabilistic polynomial over p is is the same.
No, it's not the same.
Okay.
So that's why I got a p there.
More relevant comment.
Yeah, I was anticipating this, and I'm telling you, you gotta, yeah. You learn again.
The more relevant comment.
His was for mod 2, yeah.
Shamir,
That's both.
Ali Shamir 20 years earlier had the same reduction
For mod 2.
for mod 2, which is interesting, which was, this was
Yeah.
in the context of Boolean matrix multiplication, reducing it
Yes.
to the arithmetic case, so
Yes.
that you can use the fast matrix multiplication in
Yes.
Boolean. Yeah. So it's also this
Yeah, yes.
probabilistic polynomial for end of
The random subsum trick is a different thing, yes. Yeah. Anyway, I do think that the first person that observed the generalization to mod p was Smolensky. Okay. So here's the algorithm. So we set our parameter delta to be, let's say, 1 over 100k. Okay. We're going to end up getting some algorithm like this, so that 100 will end up going there. So the idea is, given our set of polynomials, we repeat the following for some constant times n times. So we want to do something so that it will hold for all the b's. So we have some high probability statement for all the b's. We construct this random q sub s from s. So we draw a random q sub s independently for each trial. And then we evaluate that q sub s on all possible points b. Okay? So all possible p to the n minus delta n points. All right? So we get a value each time. So we do this some constant times in time. We get some table of p to the n minus delta n each time. And then we return this a solution if there exists some sort of column in this table so that it was always non-zero, say for greater than half the times. Okay? Because here, right, we have probably 2/3 of giving you the right answer. So we're just looking at it if it's non-zero for greater than half the time. So this is a two-sided algorithm, but of course we could make it one-sided by using search decision and forcing it to print something and then checking that it works. Okay? So that's the algorithm. And so, well, for one, why does it work in the desired time? So the first part is that this part 1 doesn't take too long when p is small enough, okay, because of the way I set delta and because of sort of like the number of possible monomials q sub s could have. Its degree will be smallish, and so this step is actually not too arduous. It will actually be a low order term. Now 2, this is going to more or less govern the running time here because we're looking at p to the n minus delta n time roughly. So the point is here, given the polynomial represented as a list of coefficients, you can just evaluate it on all of the points in fp to the n minus delta n, and essentially polynomial amortized time by a divide and conquer approach. No matrix mult needed for that. So that's how it runs in the desired time, and the reason why it works is just a simple Chernoff bound, union bound type argument applied to this observation here. Okay, that it's going to give me this is going to give me the correct answer about all the possible b's. Okay, so it even locates like, say, a prefix of a solution. Okay. So this is a randomized algorithm, and you can de-randomize it with some loss here. I mean, you'll have some order k, so order k term that depends on p a little bit. Just at a really high level, you can use epsilon bias generators, say for fp, to choose these polynomials. And you can use mod amplifying polynomials to compose these layers of polynomials over the integers. So that's just a really high-level idea of how the de-randomized algorithm works.
So why do you need the mod amplifying for deterministic but not for randomized?
It just turned out to be convenient, and in fact, it allows us to count the number of solutions. Yeah. Yeah. I mean, I don't know if I have like a good succinct explanation for it. Yeah, I mean, there are some limits on my ability to be succinct in one slide, but yeah.
So the trade-off is that P delta n k will equal roughly n minus 1 minus delta n.
The trade-offs?
Is that the degree of the polynomial will balance n minus delta.
Yeah. So yeah, like by setting this whatever 1 over 100 thing, this degree will actually turn out to be like sort of way smaller than like the thing. But yeah, that's the idea. Is you want to balance like how many terms you get versus like the evaluation time. That's ideally what you would like to do. Yeah.
Can you just run a PIT on QS?
A PIT. I mean, no, we have some probability of error, so like there could be many points on which it gives the wrong answer. We're not talking about it being identically zero on all points. It's like 0.4 point, it gives us the right answer with some decent probability. Yeah, that would be way nicer. I mean, some reduction to PIT. I mean, maybe harder to de-randomize, I guess, though. But yeah. Okay. All right, so that's a fairly different approach to this kind of thing. So now I want to talk about a slightly more general problem, counting the solutions. So counting the cardinality of the zero set. Okay, so we'll call this a sharp DKSP. Okay, it's the same as before, except I want to compute the cardinality of the solutions to the system. Okay, and by computing the rank of the matrix, I can also do this for linear equations. A very interesting, not well known result is that if you have one degree 2 polynomial over FP, you can actually count the number of solutions in polynomial time. And this goes all the way back, as far as I could trace back was Carlitz in the 60s, but even before that, like Dixon.
Polynomial in log P?
Sorry?
The running time is polynomial in log P?
Oh,
yes, I think so, yeah.
But this is just the canonical form of quadratic polynomials that you can
Yeah, the fact that they're quadratic, you can put them in canonical form and stuff. Yeah, I mean, that works for odd P, that makes it pretty easy. For even P, you got like, so like for power, for like characteristic 2, it's more complicated. This, I guess, why I put Carlitz there, because he actually worked for characteristic 2. Right, so you can generalize the algorithm on the previous slide to get a similar type of thing for counting. Okay. And this problem becomes sharply hard very quickly. So already for degree 2 and F2, again by natural kind of reduction. And already for degree 3 and over F2, it's still a sharply hard, even when you've got only one degree 3 polynomial, and you want to count its roots. But the reduction blows up the number of variables. So this is due to Ehrenfeuer and Korpinski. And it blows it up by quite an amount, so like maybe n cubed or something. And so the natural kind of fine-grained question is, well, how hard is it, so exponentially hard, to count the zeros of a constant degree F2 polynomial? Might we expect like say a 1.99 to the n time algorithm for this? If your reduction is blowing up by like from n to n cubed, then there's no impediment necessarily there. Okay. And so recall, finding a zero of one polynomial is relatively easy. This we can do. So it's really a problem of counting versus finding. So how hard, so finding is polynomial time. Is it exponentially hard to count or not? That's the question we're asking. So building on some work that I had earlier this year, so this is a theorem with Bryn Moore Chapman, we can prove a rather strong hardness result. So for all epsilon, so greater than 0, and c, say greater than 1, we're going to look at having systems of Cn polynomials on n variables. We're going to have a deterministic sub-exponential time reduction, so p to the epsilon n time reduction, from the counting problem on Cn polynomials to counting the zeros of one polynomial, okay, whose degree has increased slightly. This is interesting. So the thing I want to emphasize, the reason why I kept talking about the p, the factor of p, is because it's important. The factor of p is actually not here. So this is actually a fairly non-trivial thing. So we can go from a whole system of linearly many polynomials to one polynomial of slightly larger degree. Okay. So the idea is that this counting solutions to a system of degree k is fine-grained equivalent because we didn't change the variables at all, in fact. The number of variables did not change, period. We just incurred this sub-exponential type running time to counting solutions to one polynomial, okay? Now, okay, it's important to say here, you know, for completeness, if we were working over the reals, this would be really, really easy. Okay, if we're working over the reals, we could just take a sum of the squares of all the polynomials and then see if it's 0, and it just only increases the degree by a factor of 2. No big deal. Well, what's interesting is that this is working over finite fields. Okay, that's the interesting part. Okay, and it's not like just sort of doing some Fermat's little theorem trick where I'm raising something to the p minus 1 or whatever, and because there's no dependence on the field size.
So what is that fine-grained equivalent? What does that mean?
It means that they're equivalent to each other in a very strong sense, that like the parameter n. So if you had something that just barely beat exhaustive search for one equation, would already work for a whole system because the number of variables did not increase at all.
So you're not going to give formal definition of that?
No, I'm not going to give a formal definition of it, no. But you can think of it as YARS, yet another approach to refuting the strong exponential time hypothesis. So the idea is that like, so the idea is that like the k-sat problem is believed to require, say, essentially to the n time. You cannot improve on the base of the exponent, okay, even by any particular constant. Okay, this is a hypothesis, a strong exponential time hypothesis. So as k increases, it gets harder and harder, and you just for any string of 9s, you can't solve it faster. But this is saying that actually, even to solve sharp k-sat faster, it would suffice to count the zeros of a constant degree, so this constant depending on k, polynomial and n variables over f2 in, say, 1.99 in n time. Okay, so I'm like just changing the number of 9s here for that. But the point is the number of variables didn't change at all. So having even like a slightly better than brute force algorithm here gives you one in the original, for the original problem. That's all. That's all. Yes?
So it's completely analogous to what happens with k-sat, right? The previous result is like for every fixed k, you can improve a little bit on the exponent, like 1 minus.
Yeah. You can even think of this algorithm for solving systems as a generalization of k-sat algorithms. Yeah. That's a good point. Thanks. Yeah. All right. So this is a sort of very strong hardness result. Okay. So let me say how this thing works. So first, we're going to make a totally dubious assumption, no justification for it at the moment. We're going to assume the number of polynomials in our system is actually small. So epsilon n, where epsilon was something we chose. Because we're going to assume there's not that many polynomials. Okay, and then we're going to remove it. Okay. So given the number of polynomials is not too many, here's our reduction. Okay. So I'm giving you epsilon n polynomials. Okay. So let let v1 through vp to the epsilon n be a enumeration of all vectors of length epsilon n. Okay, I have two counters initialized as 0. I go through all the possible vectors in this set, so I enumerate all I. Okay, I form a linear combination of the ith vector with these polynomials. Okay, so I just take all possible linear combinations of the system of polynomials I've got. Right, this is epsilon n, the vectors are of length epsilon n, so this is just the inner product. Okay? So I'm forming this polynomial. Obviously, it has the same degree as whatever the degrees of these things were. If this is k, it's degree k. Okay? Then I'm counting the number of zeros of this polynomial. I'm adding that to some running total z. I count the number of zeros of 1 minus the polynomial, add it to some running total n. And then finally, after all is said and done, I output z minus n divided by the total number of vectors, in this case p to the epsilon.
This is an exact reduction.
It's an exact reduction, yes. Yeah, so obviously this thing is degree k if all the polynomials are degree k. So in fact, there's no change in degree here. Okay, yeah. Yep. And this is one oracle call to counting. The number of variables didn't change. Okay, so we're good. And there's another oracle call to counting. This is where we're counting. So we're making p to the epsilon n times 2 oracle calls. Okay. So why does this thing work? So let A be the set of solutions of the system. So those assignments making all the polynomials vanish. Okay. So take any solution of this. So anything that makes all the polynomials vanish makes this capital P sub I vanish. Okay? And it does not make 1 minus the polynomial vanish. Okay? It makes that polynomial 1. And that's true for all the vectors. Okay? So that means that every solution here gets summed up P to the epsilon n times in this thing and divided by P to the epsilon. So every solution contributes 1 to this running sum. Okay? And similarly, everything that's not a solution makes the vector of polynomials a non-zero vector. Okay? And I'm counting up the number of times that over all possible vectors that a non-zero vector becomes a zero vector when I take the inner product. Okay? That's going to happen exactly 1 over p of the time that it comes 0 and exactly 1 over p of the time it comes 1. Okay? So those will cancel out. So it's because I'm counting up the exact same number there, they just completely cancel. And so every non-solution contributes 0. Okay? All right. So under our assumption, this output is a correct count. Okay? Of course, we've got like epsilon in there, so we would like to have some arbitrary constant times in. Okay. So it's a very, very simple reduction. Okay. So now let's see how to reduce to the case of epsilon in polynomials. So we're going to start with C in polynomials, and we want to end up with epsilon in polynomials. So the number of solutions to the original system equals the number of solutions to the new system. Okay? So our first try is to partition a set of polynomials into epsilon n groups. So each group has, say, order C over epsilon polynomials. So just group them up naturally. And form a single polynomial, which is supposed to vanish if and only if all the polynomials vanish. Okay, so this is the first try. All right, so so people who work over prime fields, this is a very common expression that you see. This is Fermat's little theorem being applied here to make sure this is always 0 or 1. It's a very, very standard kind of trick, actually. So, but this actually gives us degree p. Okay, so that's not going to give us what we want in the end. It's going to give us, so I promise you ck over epsilon, there's an extra factor of p because there's p minus 1 there. Okay?
But even for constant p, the result is interesting.
Even for constant p, this result is interesting. Yeah, it was interesting enough for Sosa. Yeah. So the point is that so this polynomial will vanish if and only if all the polynomials in that group it corresponds to vanish. Okay, and so any solution original system is going to be a solution new system, and non-solutions are non-solutions. Okay.
Can you do some sort of a multilinearization of the thing to get rid of p?
That's not how we do it, but. Maybe you do. I mean, yeah. So this is kind of like if I took the product of them, that would compute the or, but I want to actually compute the and kind of over them. So it's a little subtle. So, yes.
So this is kind of like a disjunction. So it's if solution goes to 0 for this polynomial.
No, this is like an and.
Yeah.
Yeah. So disjunction would be easy. Just take the product of them.
Is it important for you that it's 0, 1, for instance? Like 0 and any non-zero guy, would it work?
Yeah, it's not important, and that's actually what we exploit. Right. So yeah, it's like this is sort of over-constrained because it gives us a 0, 1 value.
The determinantal polynomial does the work.
The determinantal polynomial. Okay, well, we'll see if what I've got is the determinantal. I don't think so.
Reducible, you need the reducible polynomial.
Lenin, I think we should let him finish.
Yeah, I got like a few minutes left, so yeah. Okay, so to improve the reduction, I have something called Bryn Mawr's lemma. Bryn Mawr's my PC student. So the idea is if you're given, say, 2 to the t polynomials, we can construct of degree d. You can construct a polynomial of degree 2 to the t times d, which does the job. So there's no factor of p. The way this works is it uses quadratic residues and actually non-residues modulo p. The determinantal polynomial.
Exactly construct the guy which is 1 which is 0, it's supposed to be not.
Leonid, I'll really have to cut you off.
Okay. So anyway, yeah, let me skip the beautiful proof of Benoit's theorem. Okay, so two open questions are obviously to improve this running time, improve it for like all values of p and k, which we haven't yet done. And there's some heuristic reasons to believe that actually you could improve this slightly better, and that would in fact improve the best known algorithms for k-set, whatever super strong ETH means.
But nobody believed that, right?
Nobody, that's a little, I don't know if nobody believes it, but yeah.
Okay.
Yeah, I don't know if it's a straw man either, but I don't know. But okay. Yeah, so the question is, could you do it with no blow up in the degree? Could you get a reduction? I mean, you don't have to necessarily go through algebra. You could, do some nice algorithmic stuff. So yeah, our algorithm blows up by some factor. If the answer were yes for k equals 2, if we could preserve the degree with a selection time reduction, then ETH would be false, so probably not. Mainly because counting with one polynomial can be done in polytime. So, okay. That's all. Thank you. Sorry for going.
So, Mrinal, you set up while question, yes, Avi.
All right, so do you have hardness from k-sub to improving this savings in systems of polynomial equation?
Oh, so if you could improve k-sat,
yeah,
can you improve systems?
by more than 1 minus 1 over k.
So I know that if you can improve the system, you can improve k-sat, but you'd like to know if you can improve k-sat, can you improve this? It's a good question. It's a natural one. I'm not sure. I hadn't thought about it, so we have to think about it for a few minutes. How they answer.
Okay, if not, let's thank Ryan again.